Hello, my name is Luis Serrano and this is Serrano Academy, and this video is about Proximal Policy Optimization or PPO. Proximal Policy Optimization or PPO is tremendously important in reinforcement learning and in machine learning in general, especially nowadays, because PPO is the method that is used to train large language models. See, large language models are trained using something called reinforcement learning with human feedback, or RLHF. RLHF is the topic of the next video, and it pretty much consists on training a large language model by making it play a game. And in this game, the model scores highly if the humans rate it well. And the technique used in RLHF is Proximal Policy Optimization. So in this video, I'm going to tell you everything about Proximal Policy Optimization. In short, PPO is very similar to other reinforcement learning methods like the ones you've seen in the previous video, where you have two neural networks, you train a value network and a policy network. Now what's special about PPO is that the value network and the policy network get trained at the same time. Let me show you how. So in this video, we're going to learn three things. First, the value neural network, then the policy neural network, and then how to train them. But the trick here is that we're going to train them simultaneously. So let's introduce a grid world, which is very similar to the one in the previous video. Here we have a grid and an agent that's going to walk around this grid. Now, in this grid, some cells are special. For example, here there's a lot of money, here there's also a lot of money, and here there is a dragon. So if you land in the money, you're good, and if you land in the dragon, then that's bad because the dragon will eat you. And we can put some numbers. So if you land in the money over here, you get plus 5 points. Over here, you get plus 4 points. And if you get eaten by the dragon, you get minus 1 point. And there are some barriers that you are not allowed to cross, like the one here and the one here. So the idea is that the game consists in the agent walking around the grid, moving up, down, left, or right. And when it hits one of the special boxes, then it gets that many points. So in this game, it won 4 points. If it plays again, then let's see what's going to happen now. It got eaten by the dragon, so it got minus 1 point. And it doesn't have to start in the bottom left. It can start anywhere. And let's say in this game, it gained 5 points. So the idea is to get the agent, which is that orange ball there, to learn how to play the game in an optimal way. And that grid world is pretty much the quintessential example of reinforcement learning, but you can think of many problems being solved using reinforcement learning, like playing chess, playing Go, or playing many games like Atari or Nintendo games. Also, robots learn to move using reinforcement learning, and most importantly, large language models like the ones we use all the time are trained using reinforcement learning. So let's talk about states. A state is very simple. It's any place where the agent can be. So it cannot be on the barriers, but it can be on pretty much any cell on the grid. So in other words, a state is any position where the game can be. And we also have actions. So let's look at some square like the one in the right. And let's say it has 4 neighbors. It can go up, down, left, and right. And those are the 4 actions. So the actions are basically the arrows where the agent could potentially move. Now I could simplify this and let's say we can tell the agent not to walk in the walls. So we can remove some of these arrows, and those are the available actions that one can have for each of the states. Now let's talk about values. So let's look, for example, at this cell in the middle. If the agent is here, then what do I know about the game? Well, let's say that if the game is played well, then I can reach a value of 5 from here. So that means that if I'm in this state, I can assign a value of 5 because it's sort of the best I can reach from that place. And now it's clear that pretty much any square other than the 4 and the minus 1 have a value of 5, because from any place in this grid I can reach that 5 on the top right. Now that game is not very interesting, so let's make it a little more interesting. Let's say that it costs 1 point to move 1 spot in this grid. So what happens if I'm in this spot over here? Well, I can move to the 5 and I earn 5 points. but I lost 1 from moving there, so the value here is 4. That means that 4 points is the best score that I can achieve if I am standing at that cell. What if I'm standing over here? Well, I can walk around in an optimal way in this direction, and notice that if I'm here, the value is 4, and if I'm here, the value is 3, because whatever I do, I need to do 2 steps to get to the 5, and if I'm here, the value is 2. That means if I'm in that grid, the best I can do is 2 points, which is if I walk as fast as I can to the +5. Now, what happens if I'm here? Well, I could try to walk all the way to the +5, and if I continue playing this game, then the best I can do is -4, because I lost a lot of points by walking, but then I gained 5. However, I can also just walk up and get that 4, and it's gonna be much better, because now I make 2 points. So the value here is not -4, is 2. In other words, the value is the maximum score that I can achieve if I play as intelligently as possible. Now, you may see a rule happening here, right? Let's say I have a box and it's 4 neighbors and the 4 actions I can make. Let's assume that I can make 4 actions and that I have calculated the values of all the neighbors. So the neighbors have values of 4, 1, -3, and 2. Then obviously I want to walk towards the 4, which is the highest. And then I subtract 1 because it costs me 1 to get there, choosing this action over here. And therefore, we have a rule, which is that the value of a cell is the maximum of the values of the neighbors minus 1. Using that, we can start actually propagating the cells and calculating all the values. So all the neighbors of a 5 have a value of 4. Now, among the stuff that I haven't filled, any neighbor of a 4 has a 3. Now, any neighbor of a 3 that I haven't yet scored has a value of 2. And any neighbor of a 2 that I haven't yet scored has a value of 1. And then the same thing with 0 and -1. And notice here that any neighbor of a -1 that I haven't yet labeled has a value of -2. Notice something peculiar. If I'm here, the best I can do is walk down to the -1. So I have a value of -2. But if I'm here, I shouldn't walk to the -1. I should walk to this 4 over here and get a value of -2. So those are the values. Now that you've learned what values are, let me tell you what a policy is. So let's go back to the first game where it was free to move around. Now, if it's free to move around, then I always want to get to this 5 over here, and I never want to hit the other 2 numbers. So if I don't want to hit this 4, that means I should forbid these 2 arrows that lead to the 4. And if I never want to hit the -1, then I should forbid these 2 arrows over here. Now notice that whatever the agent does, as long as it follows those arrows, it's never going to hit the 4 or the -1, and it's always going to get to the 5 eventually with probability 1. It may take forever, it may loop around, but it'll win the game. So these arrows form what's called a policy. Now let's look at a policy when you actually charge 1 point for moving to another cell. Let's remember what the values were. These are the values for each cell. So what do you think a good policy would be? Well, basically, if I put an arrow pointing to the highest value among the neighbors, that's a good policy. So if I'm here at this 1, then a good policy would be, for example, to move to this 2. I could also move to the 2 upstairs, but I'm definitely not going to move left. And if I'm here, well, a good policy is to move up and maybe right and then back up. So I think we're getting the idea of what a policy is. If I have, for example, 4 neighbors and the 4 possible directions I can go, and I look at the values and they're again 4, 1, -3, and 2, well, we saw that the value is 3, but the policy is also the arrows that point to the highest value. And I could have more than 1 arrow coming out if that highest value is repeated. So a good policy for this game would be this one. As long as I follow those arrows, I will always end up with the maximum number of points I can achieve at that particular cell. And that is the policy. Well, it seems like we solved the problem, right? Because we have calculated the values and we have calculated the policy. And with the values and the policy, actually with either one of those separately, we can win this game. So what's the catch? Well, as you may have noticed, in order to calculate the values on the policy, we had to visit every square on the grid. Not only that, but we had to visit them several times because we needed to iterate and actually recalculate these values several times until we got the perfect values and policy. Now, visiting every square on this grid is not a problem when the grid is small, but imagine a grid that is really, really large. Let's say thousands of columns and thousands of rows. For such a grid, it's hard to visit every square and even harder to visit them several times. So what could we do? And as a matter of fact, this problem can get even harder because you could have infinitely many states. For example, if you're training a robot arm at a factory, well, every position of the arm is a state and there's infinitely many, so there's no way you can visit all of them. So we somehow need to approximate the value function. And for that, we're going to use neural networks. So how is it going to work? Well, the idea of a neural network is that it sort of gives us a continuous function for the value network. What do I mean by that? Let's say we have discovered that the value on this square is pretty high. That means that the values on the squares around are probably high as well. Likewise, if a value is really low, then the values for the squares or states around them are also pretty low. So we don't need to visit all the squares. If we manage to visit a bunch of them, we are able to calculate the function for the rest, or at least approximate it. And for that, we use the value neural network. Now, if you don't know what a neural network is, I recommend this video over here that I have in my channel where I explain neural networks in detail and how to train them. But all you need to know is that in this neural network, we take the coordinates of the state or of the box, which are x and y, the horizontal and vertical coordinates, and that's the input. And the output is what the neural network thinks the value is. So in this case, for example, 3. Of course, for another problem, the input of the neural network can be larger than 2. It can be basically a bunch of variables that describe the state. And the output is the value. We're going to draw this neural network like this. In here, it only has one layer, but it could have many, many layers. It could be really large, but the input is the state and the output is the value. Now, just like we had a value neural network, we also have a policy neural network, and it's based on the same premise. Let's say that we've managed to calculate a good policy for this state over here. Notice that this policy has 4 arrows with different sizes. That means that the policy recommends us to go up with more probability than to go down. I'll elaborate on this policy in a little bit. But in other words, if the policy for this state is this one over here, then it makes sense to think that the policy for its neighboring states are also similar, right? So just like we did with the value, we can approximate the policy with a neural network called a policy neural network. And the input, again, is anything describing the state. So in this case is the 2 coordinates. And the output is the policy that's going to go in that state. Now I'm going to draw the policy neural network like this. It can also have many, many layers, but I'm going to draw just one. The input is the state and the output is 4 things. The probability of going up, the probability of going right, of going down, and of going left. In this case, let's say that the output is 0.6 for the probability of going up, 0.25 for going right, 0.05 for going down, and 0.1 for going left. This is called a stochastic policy, and I'll tell you more about it in a little bit. But the idea is that at every state, we have these probabilities of going in any of the 4 directions. And this policy hints that the value is going to be higher in the state to the top, because the probability of going up is higher. So in summary, we have the values over here, but since we can't calculate all the values because it's too much work, we use the value neural network to approximate them pretty well. And it's going to take a lot less iterations to train a pretty good value neural network. It may not be exactly the values we want, but they're going to be close enough that they're going to give us a pretty good idea of how to do well at this game. And then we have the policy over here. And since we also don't have the bandwidth to calculate all this policy, then we have the policy neural network that's going to approximate the policy really well. Now, I mentioned before that this policy on the right is different because it's probabilistic, and that's actually a good thing. You see, the policy at the left is fully deterministic, so it tells you exactly what to do. Sometimes it gives you options, but it pretty much tells you what path to follow to get to the perfect place. However, as we play this game, we don't want a deterministic policy because a deterministic policy won't explore the space very much. On the other hand, a stochastic policy like the one on the right allows us to really explore the space well because it gives us probabilities. It may not take us to the best score every time, but it allows us to walk around the grid and be able to improve our values and our policy. So a stochastic policy is always better than a deterministic one when you're training a model. You may have heard the terms explore, exploit in machine learning. The policy on the left exploits because once it finds a good path, it keeps getting that path and getting the best possible score it can from what it knows. However, the stochastic policy on the right actually balances explore and exploit because it tries really hard to get high scores, but it also allows it with a small probability to explore the entire space and be able to improve the values and the policy. And now that we have the value and the policy neural network, let me show you how to train them. Okay, so recall that we have two neural networks, the value neural network whose job is to approximate the values, and the policy neural network whose job is to approximate the policy. I'm going to tell you how to train both of them, but first I'm going to tell you how to train the value neural network. So here's the main idea for training values, and I'm going to be a little vague, but don't worry, I'll get into the details slowly. Let's say that we have a state whose value is 2. And what do I mean by the value is 2? I mean that the value neural network thinks that this value is 2. However, let's say that the actual value is 5. So this neural network underestimated the value. And so we need to tell the neural network to increase this value of 2. So we introduce something called the gain. The gain here is 3, which is the actual value minus the value the neural network thinks. And in order to tell the neural network to increase this 2, then that gain is going to become a loss function that gets fed into the neural network. Again, I'll be more specific about this loss function in a little bit. But for now, think that we're going to use the gain to tell the neural network to increase this value of 2, and then maybe it'll make it higher, like a 2.1. And in the opposite scenario, let's say that the neural network thinks that this value is 5 and the actual value is 3. So now the neural network overestimated and the gain is 3 minus 5, which is minus 2. So that's actually a negative gain. Well, we're going to take this negative gain and tell the neural network to decrease this 5 in the training. And the neural network will get something out, like for example, a 4.9. So in other words, we are training the neural network to get closer and closer to the actual values. Now I promised that I was going to be more specific, so let me be more specific. On the left, we have the values that the neural network gives. Now this neural network is not very well trained. It's on its early stages. As you can see, the values don't look very much like the actual values we calculated before. But we're going to do one iteration to make it better. So let's say we're standing at this spot in the middle. And what we're going to do is we're going to walk around until we reach a terminal state. And how do we know how to walk around? Well, we can use the policy neural network that we have so far. It may not be great, but it's going to give us some path. Now here, I was lucky and we reached the terminal state of 5, but we could have reached the terminal state of -1 or +4. It doesn't matter. The fact is that from this path, we can calculate some values, and we calculate them like we did at the very beginning. So let's mimic the path over here. And now the values for this path are a 4 because it's 1 square away from the 5, then a 3, then a 2, 1, 0, and -1. So those are the actual values. Notice that they're not necessarily the actual values. Here I was lucky that I ended up with a pretty good path. But the policy could have taken me elsewhere and I could have calculated different values that are not exact. That doesn't matter. We're going to trust that if we do this many times, we're going to get close to the actual values. Now, how do we tell the neural network how far its values are on the gray path on the left than what they should be on the colored path on the right? Well, we take the difference. and then we square it. If you've seen loss functions in machine learning, this is a textbook loss function. It's the square difference. Because the smaller the square difference is, the closer the neural network is to calculating the actual values. So let's take the differences of these numbers and square them, and we get these values over here. Now, it's a custom in loss functions to actually take the average instead of the sum. So we take the average, that means we divide by 6 since there are 6 numbers, and this sum divided by 6 is 3.36. So 3.36 is the loss, is a quantification of how bad this neural network is, because the higher the loss, it means the farther the neural network is from approximating the values, and the lower the loss, the better it is. In an ideal situation where the loss was 0, that means the value neural network managed to approximate the actual values perfectly. And just like we do with neural networks, we're gonna take this loss and use it to train the value neural network. And so after one iteration of this training, then the neural network will be able to output slightly better values for those cells and for everything around. And as you can imagine, if we continue the training by taking different paths and always training the neural network, then at some point we're gonna get to something pretty good. That means a neural network that approximates the values pretty well. And that's the value neural network. Now, if you like formulas, then here is the formula for the loss function of the value neural network. And that looks complicated, but that's exactly what we saw here. Let me show you. So this E over here is the expected value, but the expected value is nothing more than an average. Remember, this 1/6 was when we averaged over 6 numbers. Now, what is this? Well, V is the value neural network and ST is the states. So those are the values that the neural network thinks those particular states in that path are. And what is RT? Well, those are the actual values that the neural network wants to get to. Now, they may not be, as I said, the actual values, they depend on the path, but let's pretend for a moment that this is the goal of the neural network. Those are the values that it wants to get to. And finally, this squared is this squared over here. So this is, as I mentioned, a square loss function. And we use this loss function to train the neural network. If we can get the loss function to be as small as possible, that means that the values that the neural network is outputting are as close as possible to the actual ones. And that's how you train the value neural network. Now let me show you how to train the policy neural network. So recall that we have two neural networks, the value neural network and the policy neural network. And I already told you how to train the value neural network, so now I'm going to tell you how to train the policy neural network. It's a similar idea, but a little more complicated. Let's get through it. So let's say that we have two states and a policy that tells us the probability of going from the left state to the right state, and it says it's 0.2. This probability is given by the policy neural network. So our goal is to fine-tune and to train this policy neural network to come up with a better estimate for this probability. Since we're training them at the same time, let's look at the value neural network. And let's say that the value neural network thinks that the value for the state at the right is 2. And now let's say that the actual value is 5. And by actual value, I mean the same as before. We take a path, we follow it until it terminates, and then we calculate the values from there. And the path was given using the policy neural network. So again, it could be the path that gives us the best values, or it could be a path that gives us some other values. It doesn't matter for now. Now, because the value neural network thought the value was 2 and the actual value was 5, that means there was a gain of 3. In other words, the value neural network underestimated the value by 3. So we need to do two things. The one we did before, which is we tell the neural network to increase the value for the state because it estimated it as too low. And we also want to tell the policy neural network to increase the probability to get to that state, because both neural networks are trained at the same time. So they both underestimate this box. And we need to tell them both to increase the value of the box and the probability to get to the box. So the policy neural network is told to increase it, and let's say it increases it to 0.3. And that's the idea. Let's say we have the opposite scenario, where now the value neural network thinks the value is high, 6 for example, and the actual value is not that high, so it's 1. Then the gain is -5, which means it's a loss of 5. And we need to tell two things. We need to tell the value neural network to decrease the value on that state to get closer to 1. And we also need to tell the policy neural network to decrease the probability to get to that state, because both neural networks overestimated this state. And therefore the policy neural network would decrease this probability to, let's say, 0.1. And that's the idea of how to train the policy neural network. Notice that they both get trained at the same time. However, there's a special ingredient in training the policy neural network, which is impulse or momentum. Let me show you how momentum works with a simple example. Let's say that there's a kid running, that's scenario 1, and the kid is running towards the right with a velocity of 10, and we decide to help the kid out, so we push them. That means we apply a force in the same direction that the kid is running, so that increases the speed. Let's say from 10 to 20. Now let's look at another scenario. In scenario 2, the kid is running, but now they're running towards the left, and we still push them towards the right. That means that we change their direction, but the velocity obviously doesn't grow, it shrinks. Why? Because the velocity here increases a lot from 10 to 20 because we push the kid in the same direction that they were running. On the other hand, here the velocity went down because we pushed the kid in the different direction than they were running. In other words, the impulse here, or the momentum, was in the same direction as the velocity, and here it was in the opposite direction. Now obviously you know how physics work, so this is nothing new, but I'm gonna show you how this is used for the training. So let's look at scenario 1 and make a little plot. In the horizontal axis, we have the iterations of the neural network. So as the neural network is trained, there are many iterations, and in each one of them, the probability of a certain state changes. So let's say that as we train the model, the probability of a certain state has been increasing. And then we notice that there's a gain. That means we need to increase the probability for the state. Well, since it's been growing, then it increases by a lot. In the same way that when the kid gets pushed in the same direction that it's running, the velocity increases. On the other scenario, let's say the probability of a certain state has been decreasing through the iterations of the neural network. But we discover that this is a pretty good state. So we have a gain, a positive gain. That means we need to increase the probability for this action, and therefore it increases, but not very much, because now we're pushing the kid in the other direction than they were running. In other words, on the left we had an impulse as the probability is increasing, then we have a gain, and therefore the probability increases more. In the case on the right, the impulse is going down, and the gain is a force that pushes it in the other direction, so it doesn't increase that much. We also have two other scenarios, which I'm gonna tell you quickly because I know you can imagine what's happening. If the probability is increasing and the gain is negative, then the probability now decreases. On the other hand, if the probability is decreasing and the gain is negative, then the probability will decrease much faster. And this is because in the case on the left, the impulse goes up and the gain goes down, so it doesn't decrease that much. Whereas in the scenario 4, the impulse goes down and the gain goes in the same direction, so it decreases a lot more. I'm gonna kind of forget scenarios 3 and 4 numerically, but I encourage you to, if you want, pause the video and actually work them out. So now, what do I mean exactly by increase or decrease the probability at a certain rate? Well, let's say that we're training the neural network and we are at iteration 100. And at iteration 100, we have that the policy tells us that going between this state on the left and the state on the right has a probability of 0.4. And that also happens in scenario 2. Now let's say that we find a gain of 10. This means that the neural network underestimated the value of this state by a value of 10, and that also happens in the scenario in the right. So clearly we have to increase this probability. This is a pretty good state. So therefore we want to increase that p equals 0.4. In iteration 101, the probability is going to be much higher than 0.4. However, how high is it going to be? Well, that depends on the impulse that this probability is carrying. So we go back to iteration 99 and we look at what the probability was, or what the policy was, for going between these two states. Let's say on scenario 1 that iteration 99 gave a probability of 0.2. On the other hand, on scenario 2 we had a probability of 0.8. So what happens in scenario 1? Well, the probability increased from 0.2 to 0.4. That means it carries an impulse and it's going to increase a lot more. Let's say to 0.8. Because this impulse tells us that the probability is growing, then we have a positive gain and the probability grows a lot more. In scenario 2, however, the probability will grow from 0.4, but not that much. It's going to grow to 0.5. Why? Because it's been decreasing. The probability has an impulse that tells it that it's been decreasing, and then we apply a gain. That means it's not going to grow that much, because it's the case when the kid is running in one direction and we push them in the other direction. Here, the probability is decreasing and we tell it to increase. And so that's what I meant by momentum. However, let's look at the actual formula. Just like we used the gain to train the value neural network, we're going to use something called the Surrogate Objective Function to train the policy neural network. And the way we're going to encode the impulse here is by dividing. We take the probability at iteration 100, 0.4, and divide it by the probability at iteration 99, then multiplied by the gain, and we get 20. Notice that on the right, we can do the same thing. We take the 0.4 divided by the 0.8, multiplied by the gain, and get 5. So the reason this 20 is big is because we divide the 0.4 by a small number, by the 0.2. The smaller the probability is at iteration 99, the higher the surrogate objective function is. Now notice that this is 5, it's a small number. Why is it a small number? Because now we divide it by a big number, which is 0.8. So in that way, iteration 99 told us exactly what to do. If it came from small to big, we're dividing by a small number and we get a large number like the 20 on the left. And if we're dividing by a large number because it's coming from big to small, then we have a smaller surrogate objective function. So the surrogate objective function here has that momentum ingrained inside it. Now, if you like formulas, here is the formula. It looks ugly, but it actually encodes exactly this quotient times the gain. So the numerator is the probability at iteration 100, because pi is the policy, theta is the parameters, a is the action, and s is the state. And the denominator is the same thing, but at iteration 99. That's why we call it pi old. And this a of t over here is the gain at step 100. So the idea is that this entire thing, the 20, is the loss of the policy neural network. So the idea is to train the neural network to make this loss as small as possible. In other words, we use the loss to train the policy neural network. And if we can make this loss tiny, that means that we've reached a point where the policy neural network is approximating the actual policy really well. And that's how you train the policy neural network. Now, turns out that I haven't told you the whole story. We have a small problem. Let's say that given a policy, the probability of a certain action is 0.4. But now let's say that that increased drastically because in the previous iteration it was 0.0001. That ratio is 4,000. And if we multiply it by the gain, we still have a large number. And putting in a very large number into a neural network is not very good. It's going to make it a little chaotic. So we actually want this surrogate loss function to not be drastically large or also drastically small. We want it to be somewhere in the middle. So what do? Well, we're gonna clip it. Let me show you how. Recall that the numerator is the current probability and the denominator is the previous probability. That means the probability in the previous iteration of the training of the neural network. Now, probabilities are between 0 and 1. So let's look at where the ratio of these two could fall. And what we're going to do is we're gonna want this ratio to be close to 1 because in principle, these probabilities don't change very much. So let's say we make a small radius around 1 of 0.3. So the smallest possible value that we want it to be is 0.7 and the highest possible value that we want it to be is 1.3. That means that if this ratio happens to fall between 0.7 and 1.3, for example 0.9, then we keep it as it is. Now let's say that this ratio doesn't fall in our desired interval. What if it's smaller than 0.7? Well, we don't accept that and we move it all the way to 0.7. In other words, if the ratio is too small, we make it 0.7. And what happens if it's too big? Well, if it's anything bigger than 1.3, we don't accept it and we move it all the way to 1.3. So if it's too large, we make it 1.3. This is what clipping means. And we can select that parameter. In this case, it was 0.3. We can select it to be anything we want. So this is how this surrogate objective function looks when it's clipped. We're going to call it L policy clip, and we're going to multiply this probability by the gain again, and then compare it with the clipping times the gain, and then take the minimum of these two. But then what is the clip? Well, it's exactly what we said it was before, where epsilon is exactly that value of 0.3 that we talked about before. And now with this clipped function, we make sure that it's not too big or too small, and that we have a sensible function to actually update the training of our policy neural network. And now I've told you the full story because this clipped surrogate objective function is the one we use to train the policy neural network. And that's it. That's proximal policy optimization. So as a summary, you have the value neural network, which approximates the values, and the way to train it is with the gain given by this function over here. And then you have the policy neural network, which approximates the policy, and it's trained using the surrogate objective function, which is this formula over here with the clipping. Now that's it for proximal policy optimization, which is this video over here. Stay tuned for the next one where I'll show you how to use PPO in order to do reinforcement learning with human feedback, which is the way we train large language models. And as before, if you want to review the basics of deep reinforcement learning in detail, check out the previous video over here. They're all linked in the comments. And that's all, folks. Thank you very much for your attention. As usual, if you enjoyed this video, please hit like or comment or share it amongst your friends. I always enjoy reading the comments, especially if you have other topics you'd like me to teach. I get many ideas from there. If you want to tweet at me, it's serrano.academy, or if you want to check out my page, serrano.academy, where I have all these videos plus blog posts and a lot more material. And finally, if you want to check out my book, Grokking Machine Learning, below there's a link to a place where you can get it, and there's a 40% discount code only for my YouTube subscribers. So thank you very much and see you in the next video.